Chapter 9 is such an important chapter about cycles, specifically working with ideal gases and cycles. I'm going to create three worked out example problems from textbook problems. So let's go ahead and get started. Okay, I'll try to quickly read this problem. It's problem 9.1 in the textbook. At the beginning of the compression process of an air standard Otto cycle, P1 is 100 kPa, T1 is 300 degrees K. The compression ratio is 8.5, and the heat addition per unit mass of air is 1,400 kilojoules per kilogram. Here's what we need to find: the net work in kilojoules per kilogram, the thermal efficiency of the cycle, the mean effective pressure. What's that? Hardly ever heard of that. And the maximum temperature of the cycle in degrees K. All right, so let's go ahead and get started with solving this problem. Let's look for keywords and clues in the problem statement itself. Okay, keywords that I see immediately is air standard. That's all about chapter 9. And also the words Otto cycle. Both of those are clues. Air standard, here's what air standard means. So the word air standard means model the air as an ideal gas with variable specific heat. You say, oh, okay, not exactly sure what that means. Well, here's a translation. It means use table A22 for air properties, because air properties like U and H and some other properties are tabulated there for variable specific heat. What does Otto cycle mean? Okay. At this point, now you might not be able to figure out totally on your own, but I'm going to try to help you get the ability to create the pressure volume diagram from your head based on your understanding of how a spark ignition engine works. So some folks are going to be, oh yeah, I've worked on car engines for years. I'm pretty familiar with that. Others, maybe not so much. That was me. My dad was an engineer, but I did not have a great interest in working on car engines. So there's going to be various levels of understanding of how the Otto cycle models the spark ignition engine. And I'll try to review that. Okay, and so let's see if I can help you figure out what the Otto cycle looks like on a PV diagram, so that everybody is going to be on the same footing. And so here's a little schematic. Let's start with a sketch. Here's a schematic of your standard internal combustion engine piston and cylinder. It's fitted with a spark plug up top at the top of the cylinder. And so the model, the closed system, is the air contained within the piston and cylinder. Thus the idea of maybe this is why we were working on so many piston and cylinder problems early in the semester. Okay, let's work on drawing the pressure specific volume diagram for our Otto cycle model of the compression of the spark ignition cycle. All right, so let's start with the compression stroke. So imagine the piston all the way at bottom dead center. That's where the volume of the air is at a maximum. Compression stroke. I hope everybody's heard of that. There's a compression stroke where the piston compresses the air in the cylinder up to a higher pressure and temperature. At that point, the fuel, maybe due to fuel injection, is injected in and a spark plug goes off. The way we model this thermodynamically is when that spark plug goes off for our spark ignition model, we consider that the pressure, the combustion happens immediately, instantaneous combustion. And so therefore, before the piston has a chance to move, the pressure and temperature of that air goes way up, dramatically up to pressure 3, okay? And so that's our model for heat addition, instantaneous heat addition before the piston has a chance to start moving, okay? Well, all right, so we've got this high pressure and temperature inside our system. We've got the expansion stroke. Some might call it the power stroke of the piston. We're getting work out of the piston and cylinder. getting work out. So the pressure's going down, temperature's going down until the piston reaches bottom dead center again. Looks like I forgot to mention that the minimum volume, when that spark hits, basically the piston is at top dead center, right about at the minimum volume. All right, then our power stroke. Our heat rejection model for our thermodynamic model is simply heat rejection of the air contained in the piston cylinder from 4 to 1. Now, people that work on engines know that the physical model for this is an exhaust stroke, where we exhaust the exhaust products from the valve and then bring in a new set of air called the intake stroke. But this is our thermodynamic model of our Otto cycle. It is my hope that spending just a couple of minutes that we spent here, you can generate this PV diagram from your head, not from drawing it on a formula sheet. That's my hope. All right, more key words. Okay. Given in the problem, the compression ratio is 8.5. That's very important. That's going to be R in your book, and we'll talk a little bit more about that. Compression ratio is the ratio of the maximum volume, bottom dead center, divided by the minimum volume, top dead center. So it's a volume ratio. Another thing that's given, it says the heat addition per unit mass is 1,400 kilojoules per kilogram. That is definitely going to be needed for us to solve the problem. And what that means is that's going to be a measure of Q sub H. Remember in your heads, little q sub H is capital Q sub H, heat added, divided by the mass of the air in the system. Units will be kilojoules per kilogram. Okay. This given information in this homework problem makes it different than mimicking formulas that are given in the book, because the given information is slightly different than, let's say, example problems given in the book. So that's why I'm going to try to help you get through this problem 9.1 on your own, being able to figure it out on your own. All right, so let's write down what's wanted. Let's start planning our work. Let's plan our solution. Part A, the net work. I hope you've got a picture in your head of the PV diagram. You say there was a couple of situations where either work is done or work is needed. We'll add those two up to get the net work, W net. Part B, thermal efficiency. Thermal efficiency. That's going to be energy sought over the energy that costs. Well, common sense. The energy sought, what we're trying to do for our internal combustion engine is get W net. And what does it cost us? Well, we've got to buy fuel for our engine. That's QH, heat added. So it's easy to figure out what the thermal efficiency is without going to a formula sheet or power cycle. Part C, a little tougher, mean effective pressure. I'm going to have to tell you, because I didn't pay much attention to my dad working on the car engine. I had no idea what mean effective pressure was until I stepped foot in one of my final thermodynamics classes. So we're going to study what mean effective pressure means. It's going to be little W net divided by the displacement volume. That's the change in volume from bottom dead center to top dead center. And so we'll talk about that a little bit later. And then part D, it turns out that you're going to need part D first in order to get the other questions, parts A, B, and C. And so that's sort of a key. That's sort of an interesting part of 9.1, the way the author has arranged what was wanted. A little studying, you're going to say, oh, I need part D first. Air standard cycles. What I'd like to do, I've created a little 28-minute video. If you would suggest you maybe browse it, go to Jay's Toolbox YouTube channel, click on the Air Standard Cycles playlist and see if you can fish out the Air Standard Cycles intro. A quick friendly reminder, maybe something might be a little hazy in your head. We'll blaze through this. Remember that little qn, what's the definition of little qn? Well, that's capital Qn, kind of like what you learned early in the semester, divided by the mass. Okay, So the units of little q in and little w out is going to be kilojoules per kilogram. And what you learned early in the semester, capital Q in, capital W out, kilojoules, mass, of course, kilograms. Therefore, little q in, little w out is going to have units, kilojoules per kilogram. And so in this problem, little qh is given. So be aware of that. Okay, a quick crash course in the difference between air standard, that's this problem we're covering, versus cold air standard. That's going to be the next problem we solve. It's going to be the same words. We're just going to use the cold air standard model. So for this one, for this problem, air standard means treat air as an ideal gas with variable specific heat. Translation, use table A22 for the properties you need to determine. Okay, and then this is not a visual summary of what I just said. Let's see, for any ideal gas, air standard or cold air standard, Cp minus Cv always equals R. Also, K is Cp over Cv. For air standard, we don't use K because Cp is a variable. Therefore, K would be a variable. All right. So for any ideal gas with variable specific, we're going to, you can see where we're headed. We're going to be looking for delta U. So things like maybe U2 minus U1. That's the integral of CV dt. We have table A22 frees us from having to do a complex integral from T1 to T2. So we're simply going to look up U2 and U1 as numbers, as values out of table A22 when we need them. Okay. Another really important part of air standard cycle analysis for isentropic processes with variable specific heat, two important fundamentals that are covered and derived in your book. These variables, PR1 over PR2 equals P2 over P1. And for this problem, little v R2 divided by little v R1 equals little v2 over little v1. And interesting thing here is this is going to be the reciprocal of the compression ratio. V1 over V2 is 8.5 for this problem. These are properties. VR are properties at the given temperature, at the temperature T2 and T1. And your book does a very nice job of deriving what this means. I won't take the time or bore you with deriving these fundamentals, but they are fundamentals for isentropic process for ideal gas with variable specific heat. VR2 over VR1 equals V2 over V1, only for reversible adiabatic processes. Okay, you want a little bit, learn a little bit more about Otto cycle calculations. I've got a 47-minute video with a couple of more worked out problems under my Air Standard Cycles playlist. All right, let's see. Part D, where is the maximum temperature? Where is that on my PV diagram? I'm going to suggest that you can visualize where is the maximum temperature of my cycle without memorizing what it is. Okay, I have drawn in 3 hyperbolas, lines of constant temperature on the PV diagram for an ideal gas, 3 hyperbolas. So with your eyes, which hyperbola would represent the highest temperature? The answer is the top hyperbola. What's the hyperbola? Well, remember that PV equals RT for any ideal gas. So that says that for any constant temperature, an isotherm, RT is a constant, so PV is a constant. That's visualized by a hyperbola on the PV diagram. And so quickly, without memorization, you should be able to observe that T3 is where the maximum temperature is going to be. So part D, I need to figure out what T3 is. That's the maximum temperature. Okay, let's see. What's next? Planning our work value. So once we found T3, we're going to have to figure out the net work. So we'll have to look at where are my work values. Let's look at process 1 to 2. The compression stroke reversible adiabatic. Do you see that the work, little w from 1 to 2, it's the integral of PdV. I can area under the curve. I can see it with my eyes. The work from 1 to 2 is a negative number. Work is required. That's the compression stroke. Okay. That's why I keep harping on visualizing the work for a closed system as the integral PdV, area under the curve. What's the area under the curve for process 2 to 3? That's 0. There's no area under the curve. That's the heat addition process. Makes sense. We're lighting off the fuel and air mixture with a spark. We get an immediate increase in pressure, but the piston doesn't move. No work. 0. 3 to 4, that's the expansion stroke or the power stroke. Do you see with your eyes that I'd better get a positive number from 3 to 4, reversible adiabatic expansion, and then the cooling process 4 to 1. And we're not even going to need to mess with process 4 to 1. There's nothing asked about process 4 to 1. We're not even going to have to mess with that. Okay. Another thing to observe, the compression ratio little r is given as 8.5, and that's simply going to be V1 divided by V2, which also, of course, equals little v1 over little v2. Let's remind ourselves, Otto cycle fundamentals. This is going to help us learn what's the thermal efficiency of the Otto cycle or any air standard power cycles. Energy sought over the energy that costs. We're trying to make net work. That's our objective. What's it going to cost us? QH. So the thermal efficiency is little W net divided by little QH. I had to go into the textbook to get the definition of mean effective pressure. And the mean effective pressure for an internal combustion engine is defined as the net work for a cycle, W net, divided by the displacement volume. That's going to be little v1 minus little v2, the displacement volume, the change in volume from min to max. Okay, so that's back to basics. That's reminding us, how do we get all the stuff we're looking for? All right, so what's our approach? Before we put pencil to paper, what's our approach? We started with a sketch. We wrote down our work values to make it easier on ourselves. We're going to refresh our memory that for a closed system, PV equals MRT, or in other words, P times little v equals RT. Okay. And let's see, the first law, capital QN minus capital W out equals delta capital U, or M times U final minus U initial. All right. And so those are our basics. And I created a little table for myself. Let's see, QN 1 to 2, that's 0, reversible adiabatic. 2 to 3, that's QH, that's where the heat's added. We're going to need that for thermal efficiency. 3 to 4, reversible adiabatic, QN is 0. And let's see, 4 to 1, oh, I've got a capital QL. I should have written in little QL there. Okay. How about W out? 1 to 2, less than 0. I'd better get a negative number. 2 to 3, 0. 3 to 4, bigger than 0. 4 to 1, 0. And so that's going to lead me to get thermal efficiency. All right, so planning ahead before we put pencil to paper, all I've got to do is get these two work values, add them together to get W net, QH. That's given. All right, that's a number. Okay, so then I'm done with thermal efficiency. Also, I've got the compression ratio given. All right, where do we start? Now we're about ready to put pencil to paper. Where do we start? We study the given information. We see that at state 1, the beginning of the compression stroke, P1 is given. R I can find, it's air, it's known. T1 is given, so I can immediately solve for little v1 numerically. Wow, well, the compression ratio is known, so finding v2 is going to be very easy, isn't it? It's going to be 1 over 8.5 times little v1. Okay. One of our last planning aheads, we've got 2 isentropic processes, 1 to 2 and 3 to 4. Here's what we're going to do. Let's see. We've got the specific volume ratio. VR2 over VR1 is going to equal little v2 over little v1, and also VR4 over VR3. Well, that's known. That's little v4 over little v3. Go back to our sketch. Well, how am I going to get v4 and v3? That wasn't given. You look at the power of the sketch is you're going to see that v4 over v3 exactly equals v1 over v2. So I hope that planning helps. So we're going to use these VR lookup values. These are properties. VR is a property. We're going to look that up in table A22. So here we go. I've spent all kind of time planning, but I hope you're going to see that it's going to pay off. Okay, so let's see. You should know by heart R is R bar over the molecular weight. R bar is 8.314 kilojoules per kilogram degree K. Molecular weight of air is 28.97. You do that quick math, and I have entered. I solved my problems in Excel, so you see that I've plopped down R for air is 0.287 kilojoules per kilogram degree K. I've entered my given information, P1, 100 kPa. Immediately transfer bars into kPa. T1, given 300 K. I've written those down. There's given. I turn them yellow. I calculate V1, little v1, ideal gas equation of state, 0.8610 cubic meters per kilogram. Oops, there's a typo. That says M*3. That should be meters to the third per kilogram. Sorry about that. Okay. Our compression ratio, 1 over the compression ratio. So I'm going to need that. So so what's V2? Little v2 is 0.1013, which is V1 over R. Okay. So it's 1 over 8.5 times V1. So I calculated it with units. Shame on me for not putting units of V2, cubic meters per kilogram. Okay, what's next? We're going to analyze isentropic process 1 to 2. How will we do that? Let's see. We're going to use the fundamental V2 over V1, and I haven't written it down. V2 over V1 equals VR2 over VR1. Oh, I did write it down. Here it is. VR2 equals VR1 times V2 over V1. So I did write down my fundamental in my solution. But I need VR1 first. So I'm going to go to my table, A22, and I'm going to write down, and looking ahead, I'm going to use the first law. This is a thermo class. I'm going to be using the first law. So I'm going to write down U1 and VR1 from the table, 214.07 kilojoules per kilogram, VR1, 621.2. Write those down. V1 over V2 is 8.5, given, compression ratio. V2 over V1, I cranked that out. That's 1 over 8.5. And so I'm going to solve for VR2. It's the number 73.08. Goody, yay. Okay, I've got VR2. So now what's next? Now that I've got VR2, what do I do with it? Do you see that I go back to table A22 and I find the temperature and internal energy that's associated with VR2? Okay, so I have to go back to table A22 and shop for VR2 is 73.08. Okay, and so I'm looking in table A22. Here's VR over in the right half of the table, and I'm in between these two numbers. So for my solution, I set up an interpolation table, in my case in Excel. You can do it with your calculator or however you solve the problem. I put in my VR values. I wrote in my VR value, and I did a straight linear interpolation to find T2, 688.22, and U2, 503.06. Straight linear interpolation, and there they are. Well, now, so what? Okay, big deal. Now I can use the first law for process 1 to 2, reversible adiabatic. Q is 0. So the work out is simply U1 minus U2. So Q minus W equals U2 minus U1. I flip the signs, and so I solve for W out is negative 289 kilojoules per kilogram. So I write that down. That's critical, isn't it? We're halfway there on W net. Okay. I wish there were people on the calls. Any questions, stuff like that, but we're going to move on. You can, if you're confused, you can pause, go back, et cetera, et cetera. All right, next we're going to analyze the heat addition process. That's where the spark lights off the combustion, okay? And it's pure heat addition. There's no work done, all right? So let's see, what would I do for that? I'd write the first law, okay? I'm going to write the first law, and what that enables me to do, I have to do some head scratching. I write the first law. I just found U2, didn't I? Okay. And so I can solve for U3. If I write the first law from process 2 to 3, do you see that I can solve for U3? It's the only way I can approach it because Q from 2 to 3 is given, 1,400 kilojoules per kilogram. Work is 0. I'll solve for U3. So numerically, it is, so pardon me, I've got another typo. Look at this, 503.06. That's not U3, that's U2 from previous work. Sorry about that. That should be U2, 503.06. So I'm going to solve for U3 in the first law. So U3 is Q from 2 to 3 plus U2. Gosh, how embarrassing. Should be U2. So I'm going to solve for U3, 1903.06. Oh, goody. I found U3. So what? I've got to go back to table A22 and start shopping in my internal energy column for 1903. And darn it, I don't see 1903, but I do see numbers that straddle it. Okay. So I'm going to set up my interpolation table for U3. Wrote those yellow numbers down that are given. Here's my value for U. And what am I interested in? I'm asked to find T max, so I better write down the temperatures, 2200, 2250 to find my temperature. And also looking ahead, I've got to study the isentropic process 3 to 4. So I know I'm going to need VR, so I'm going to determine that as well. So here's my interpolation table. There's my U values that I just found. Temperature value, so interpolate 2231. That's part D, check. The maximum temperature is 2231 degrees K. And VR, I'm going to find 1.92 is VR3. Okay, sorry about the typo for U2. Now we're going to move on to analyze isentropic process 3 to 4. That's the power stroke, the expansion stroke. Okay, let's see. So we're going to solve for VR4. So what's the fundamental? The fundamental is VR4 over VR3 equals V4 over V3. So I have written down my fundamental in my solution. Okay, so I realize, okay, and I just found VR3. There it is. I wrote it down, 1.919. And U3, I just found it, 1903.06. I just looked it up. Okay. So I solved for that with the first law. So I've got U3 and VR3. So I solve for VR4. Oh, well, I need V4 over V3. That's 8.5. That's given. Here's a little V4 over V3. You see that V4 over V3 is simply V1 over V2. That's the compression ratio, 8.5. Solve for VR4, 16.31. So big deal. What's VR4? Well, VR4, I can go back to table A22. I can shop for VR4. Oh, okay. Here's the two numbers that straddle 16.31. I've got another linear interpolation, and I've shown it here in my solution. There's my VR values, linear interpolation for T, 1154. He said, I didn't have to find that. You don't have to find that. But you do have to find U4 892.95 kilojoules per kilogram, because you're going to use the first law for process 3 to 4 to get W from 3 to 4. So here we are. First law, process 3 to 4. Great. I found everything I need. Ooh, I think I did okay on my solution. U3, 1903.6 from previous work. 892.95, just found it. Let's see. First law, Q in is 0 from 3 to 4. So W out from 3 to 4 is U4 minus U3, right? 1010.11 kilojoules per kilogram. It's a positive number. Yay. So I can write down both of my work numbers, kilojoules per kilogram, add them together. So all of a sudden, things are coming into place. W net is 721.12. Woo. Okay, we're almost there. We've got part A. There's the net work in kilojoules per kilogram. Thermal efficiency. Wow, that's going to be really easy. W net we just found, QH, given thermal efficiency 51.5%. Now we're really flying along. Part C, the mean effective pressure. Openly admit, don't have mean effective pressure in my head. Have to go back to the textbook to remind myself the definition of mean effective pressure. Network for the cycle, just found it. Displacement volume. Well, we've got that from previous work. We've got V1 and V2 from previous work. Okay, so the difference, and so V1 minus V2 is 0.7597. W net, just found it. So the mean effective pressure is 949. So we're going to check our units. We're going to check our units to see that the mean effective pressure is 949.2 kPa, kilonewtons per meter squared. And it asked for, the textbook asked for the answer in bars. So we'll simply divide by 100 to get 9.49 bars is the mean effective pressure. So here is our recap of this problem. Net work, just found it. Thermal efficiency, just found it. Mean effective pressure, 9.49 bars. Woo! We've got agreement with what the textbook says the answers are. And the maximum temperature in the cycle is 2231 degrees K. We found that first. Okay, so one last thought before I go on, and to show you how to solve this problem with the cold air standard model. And students may say, you know, there are a lot of formulas given in the textbook for the Otto cycle and other cycles. It's a lot easier just to use formulas out of the textbook. I got to tell you that in preparing for quizzes and tests, this is the best way for you to solve these homework problems, because you're preparing yourselves to do well on the tests, to do well on the quizzes, and also to perform well as a practicing engineer. So this is your best formula sheet. If you're allowed to use a formula sheet, well, go ahead and use it as a crutch. But look, it's going to pay off for you to do the best you can to get these fundamentals into your head. So that's what I've got. There's my solution, a couple of typo blunders. I hope it's helped. And check out the next video where I solve exactly the same problem using the cold air standard model.